All right, welcome to Thursday, week 2, ISFDB. We're going to talk a little bit more about ray tracing, I guess, and then we'll probably need to talk about rasterization as well. Just normally you talk about rasterization before ray tracing, but I don't know, it tied in, this kind of thing tied in really nicely with discussion of VVHs. So yeah, we did ray tracing first. It's fine. For events, is there something that's always running just listening, such as every frame? Yeah. So there's really two ways of doing events. One is by polling. Polling means every frame you're like, is the mouse pressed? Did I receive a network packet? Is the key pressed? That kind of stuff. You need me to make some numbers for you for long division? Yeah. Okay. Let me pause the recording.
9 questions.
9 questions. 1 second. All right. Made some long division problems for my daughter. All right, so yeah, so polling is when some part of the system is going like, is the key pressed, is the mouse pressed, is a network packet received, that kind of stuff, and it checks every frame over and over again. The downside to that is that you're going to be burning CPU cycles, especially if you have to do something like, is mouse 1 pressed, is mouse 2 pressed, is mouse 3 pressed, is the Q key pressed, is the W key pressed, is the, you can add, there's 100 keys and I don't know how many mouse buttons we have these days, 10 or 20 or something. So you can actually burn quite a bit of CPU power, and when you're doing absolutely nothing, And so a common approach is to do interrupt-driven programming. And so what you do is you set up an interrupt, so your operating system will register an interrupt. So you say, when a mouse is clicked, notify me. And then the person clicks the mouse, the operating system, there's an interrupt handler in the hardware. And so when you click the mouse, it triggers an interrupt. It doesn't have to sit there and poll. The operating system's interrupt handler is invoked. It figures out that it was clicked inside of your program, so it dispatches the event to your program. Your program gets a mouse down event. And if you have a event handler set up to handle a mouse down event, then that gets called and says, hey, they clicked. And when they release the mouse button, they get a mouse up event. The same thing happens. And so you can write one event for like when they hold down, one when they release, or you can just do it on release or something like that, or on mouse down. And that way you don't have to sit there and pull every time. So those are the two main approaches for handling events. But that's at a level you don't need to worry about. In Unreal Engine, you just set up an event like event hit, and the event hit comes about through the collision engine, like this kind of stuff that we're talking about, where you're talking about the all the different ways that things can hit each other. Did I touch a cylinder? I was actually looking through how other people did collision detection last night, and it was actually pretty close to what I was talking about. For the line intersection, what they did for like 2 line segments intersecting, that's actually a ray, but whatever. If you have 2 line segments that have a start and an end point, then what they do is they define the line segment in terms of the starting point and the slope. And it goes from 0 to 1. 0 is one endpoint, 1 is the other endpoint. And so when a line crosses it, the intersection algorithm returns a number from 0 to 1 if they cross, or it'll be negative if it's like down here, or it'll be positive if it's up here, or if it's parallel, it won't cross at all. So so that's an easy way to see if 2 lines cross. If you define it in terms of a starting point at 0 and an ending point at 1, then when you do the line intersection algorithm, you get a number from 0 to 1 if they cross, less than 0 if they're on one side, greater than 1 if they're on the other side, if they miss. So that's it's the same algebra, just kind of phrased a little bit differently. Okay, is a circle more expensive than a rectangle? Nah, not really. Rectangles and circles are both very, very, very easy. For rectangle, you have to, like, if you want to see if 2 rectangles touch, you basically say, is my minimum x bigger than their maximum x? Is my minimum y bigger than their maximum y? And then vice versa for the other way around. And so if any of them have a maximum smaller than their minimum, or a minimum bigger than their maximum, which is the same way of saying the same thing, then they don't touch, right? If my maximum is smaller than your minimum, right? Like, let me just put you there. Right, so if my minimum x is bigger than your maximum x, they don't touch. Or if my maximum x is smaller than your minimum x, they don't touch. Or if my minimum y is bigger than your maximum y, they don't touch. Or if my maximum y is smaller than your minimum y, they don't touch. Otherwise, it touches. Okay. So that's how you can do a rectangle. It's four if statements, something like that. Or you can do the line intersection test if you want. So if statements are not cheap, or they might be cheap, but they might not be. And so an if statement could be 8 cycles if you get a branch prediction miss, something like that. So call an if statement like maybe 4 cycles on average cost, something like that. It's about the same as a multiply. And add or subtract is 1 cycle. A cycle means like if you have a 3 gigahertz CPU, it gets 3 billion cycles per second. Clock goes high, clock goes low. That's 1 cycle. If your system runs at 4 gigahertz, then it does 4 billion cycles per second. But an addition is always like 1 cycle, and a multiply is always usually around 4 cycles. Subtraction's 1 cycle. An if statement, it depends. There's something called branch prediction. But if you want to put it at like 8 cycles, that's one way of thinking about it. So you do less of them. A square root's around 80 cycles. And so that's one of the reasons why taking CSI 45 is so useful, is because even if you don't do assembly programming, you sort of learn to think about the cost of things and be like, all right, what's faster, a AABB check or a circle versus circle check? So the circle versus circle, you have the radiuses. Those are probably written down somewhere. The points are written down. So you're going to have to do the hypotenuse. You're going to do a hypot. The hypot is, but you're not going to do the square root, remember. You're going to keep the square. So it would be an add, 2 subtracts, 2 multiplies. So 11 cycles. 11 cycles to do a circle versus circle. As long as you don't do a square root. If you do a square root, tack another 80 onto that. Increases the running time by 10 times. Ish. 8 times. Whatever. And a comparison. Well, yeah. And a comparison. So 18 cycles. And whereas this is 4 comparisons, so 32 cycles, but it really depends on your branch predictor. If you give a cost of 4 cycles per one, it's 16. So it's somewhere in the range, and it boils down to like architecture issues of like how accurate is your branch predictor. A branch predictor means like if you have an if statement, like if do this, else do that. So there's 2 ways your code can go. The CPU has to pick one of those ways to guess that it's going to go, or maybe it does both. Whatever. But depending on how accurate you are at guessing which way the code goes, if you're wrong, you've done all this work, you have to throw it away. If you're right, then you keep it. And so it depends on how accurate your branch predictor is. And so it gets really murky because there's a lot of different CPUs out there. They run at different speeds. They have different quality branch predictors on them. So just as a eyeball cost of 4 to 8 cycles, something like that for an if statement. So basically the AABB test and the circle versus circle test, they're roughly the same, depending. Okay. So the rendering of a ball versus a box. Yeah, rendering a ball is way more costly. A square, a rectangle could be rendered in 2 triangles, right? So drawing it to the screen, right? Every rectangle that could be drawn is just it's snapping to grid, whatever. You know what I mean? It's 2 triangles, right? Hate it? Do you know how you can take 2 triangles and make a square out of it? Or a rectangle out of it? Yeah. Whereas with a circle, if you're trying to approximate a circle with triangles, you use lots and lots of triangles, right? And so, rendering a ball can be way more costly. But we're talking about collision here. And so, like I said, with my mecha, I had 1 big ball for the whole thing, and then if that was hit, then I had 2 smaller balls, 1 for the upper part, 1 for the lower part. So, a mecha like that, it wouldn't work very well. But for the one I had, it was accurate enough, and it was easy to code and fast to run. So. Okay, so let's talk about rasterization, I guess. Do you guys understand BVH? Like, you got one big box, and if that box is hit, it checks the children boxes, and if that's hit, it checks the children boxes. And it goes all the way down until it either hits something or misses something. You guys understand that? And then your RTX hardware will accelerate that. And it's more than just a single thing. It'll do things like reflecting off, refraction, reflection. Sometimes you'll send 7 photons per pixel, so that if things scatter in different directions, you'll get more accuracy. You want your hardware to accelerate that, yeah. For a long time, ray tracing was the kind of thing that you would do to like make a nice, pretty image. It would take 5 minutes, to do a little pretty image, like. So the classic sample thing would be, like this. This is your classic ray traced image. So you'd shoot a ray out from every pixel on the screen, and if it hits nothing, I guess they just draw white here. So they shoot a ray out, hits the sky, cool, easy, easy test, white, done. But if you hit the glass ball, okay, you can see the ball reflects some light and it refracts some light. So you hit there, you do a shadow ray to see if it's lit, and then you reflect off the surface, and then you have a second ray that branches off from it that goes inside, and then when that hits the inner layer of the sphere, again, it's going to reflect and refract, and you keep doing that until you've hit some limit on the number of bounces that you can have. And all of those rays sum together to get the light at that pixel. So if the thing scatters like 20 different rays, you add and average together the results of the 20 different rays. And the more rays you shoot out, the more precise these things are. You can see over here that the reflected images are kind of rough a little bit, or they're not really anti-aliasing very much. But you can see the cylinder here is doing refraction, and you can see they're reflecting the lights from behind the camera over here. And so this is your classic ray traced image. And these things would typically, this is actually, I've read this before. Let me actually post this on, let me post this on the chat channel. This might be a fun project for you guys if you're interested in it. It's $3, and it walks you through writing a ray tracer. It's not really that hard, and you'll end up with, this is nice, But these things will oftentimes take like 5 minutes to render. Can't use it in a video game, right? And so for a long time, that was the prevailing wisdom, right? Like, you could use this for Pixar, because they have rendering farms that shoot photons out, all night long, and then when they come back the next day, they check the results and make sure it looks good, and then they move on to the next couple frames of Toy Story or Cars or whatever it is they're working on. And nobody would ever think about using it for video games. But then NVIDIA's like, all right, yeah, we can do it for video games. Our cards are fast enough now, and as long as people use BVH, which is fairly easy to reverse, it's a login, lookup time, we can do it. And so now we've got this RTX, we got this like RTX ray trace accelerator, and it looks pretty good. Like here, the rays are hitting the water, and the water is reflective, so it bounces off and hits this. And you can see it's not doing screen space reflection. One of the biggest issues I have with reflections in most video games is that it only reflects things on the screen, right? So it would reflect the axe down, but anything off screen isn't getting rendered, and so it wouldn't reflect in the water. And so you'd look up and the thing would appear. You look down, the reflection vanishes. With RTX, it has the whole scene there, and it just shoots rays out, and it sees what it hits and renders it. It looks pretty good. Looks pretty good. Minecraft looks pretty good with RTX on. There's a great talk by the people that did the Quake 2 RTX conversion. So Quake 2 is an old game. It came out in like 98, maybe? When did Quake 2 come out? 97. December of 97, yeah, so close to 98. It's not a very beautiful game, but the RTX conversion is actually really nice. It still has the old jaggedy graphics, which are a little bit jarring because the game looks really nice. It's got global illumination, so that means light comes in and it bounces around and stuff like that. Yeah, this is the scene they used. And so they go through the rendering of this scene. So light's coming in here. There's some emissive light sources over here, and they go step by step through what it took to go from the original to like this really nice global illuminated global illumination scene. Yeah, here. Yeah, so you see this? This is a better version of the other one. So you see there's shadows being cast by the emissive light sources here. You got light coming in here, and it's bouncing around, illuminating the whole room. Yeah, and so yeah, I played it a little bit. It's not bad. It's not bad. They've done a pretty good job with it. So the talk is here. No, it's just a video of it. Actually, that. Might be fun. Source engine, you got used to look at the same reflections and puddles. Yeah.
What was that?
It's a video game. Yeah, the particle effects are still pretty bad. Let's see if I can find that talk. Go to RTX talk. I watched the whole thing. It's really good. I'll try to find it for you guys. But they go through the whole process. It's really interesting to see how they did it, what problems they encountered, how they resolved it, stuff like that. Quake couldn't run on the school's old setup. Yeah, the thin clients. That was so terrible. Nowadays, Mason, we've got gaming laptops for people to take this class. So you can actually rent like a nice laptop as long as you're taking game development. Okay, so let's talk about rasterization. So let's go backwards in time. So yeah, ray tracing used to be the slow but non-gaming thing, and now it's kind of used in video games. So let's talk about a triangle. So we got a triangle. Let's not even talk about 3D for now. We'll get to 3D in a second. Let's say we got a triangle, and we want it to be filled with color. How do we fill? Is there a fill tool there? Why is there no fill tool? Well, whatever. Let's pretend. I'm just going to fill it in using a marker. There we go. It's filled with blue. Ah, damn it. Whatever. We want to draw this red rectangle. It's filled with red. Whatever. And every pixel on the screen that's within the triangle should be drawn as red. So how do we do it? What's a simple way of rasterizing it? Rasterization is one of those cool words that make you sound smart when you say it, but it's something that we all kind of know what it is, even if we don't know the term. Rasterization means drawing all the pixels to the screen, basically. So given a triangle, fill all the pixels inside it with the triangle's color. Okay. We're not even talking texturing. We're not even talking lighting. Just we have a solid red triangle. We know what the points are here, and we want to fill every pixel between these three lines with red. Just 25500, just red. How do we do it? It becomes a rectangle? No. That'd be rectangularization. No, it's rasterization. So rasterization is how we went from the wireframe world into the 3D world. There were actually 3D video games back in the 80s, and they looked kind of cool. Like if you've ever seen the Vaporwave aesthetic, it uses wireframe, and that's because rasterization is expensive, or by comparison, expensive. So they would typically just draw the outlines of the triangles, right? If you have a triangle, you just draw the three edges, and there you go. And you can actually have a perfectly workable 3D game, and it's actually much faster if you're not rasterizing it. If you don't have to fill these triangles with this color, you can actually do it much quicker, right? What's some of those games be? Like the original Star Wars arcade game. When did that come out? 1983. Wow. Okay. Any screenshots of it? Look at that. Isn't that cool? So you got text, you got a HUD, you got 3D over here. The thing scrolls past you.
What's that?
That's Star Wars. It's a Star Wars video game. 1983, really? That's amazing. Yeah. And
Has it been really popular?
I played it. Yeah, I played it a fair bit. Yeah. It's a 3D flight simulator back in the 80s, like mind blowing. But it's not rasterized. You see this? Like it's not filling the triangles or rectangles with pixels. It's just wireframe, right? So when you still put things into wireframe mode today, just why is this? If you want to see how many triangles you have, that's an easy way of eyeballing it. If you have Unreal Engine open, you can just click on wireframe mode, and it'll show you. You just kind of look at it, like, okay, that's not too many triangles, not too bad. Okay, it's a fair number here. It's a bunch of triangles back there, So rasterization. How'd you guys do it? And yeah, if you wanted to make a game with vaporwave aesthetic, like it's actually fairly popular these days. I think like people like kind of dig that kind of retro look. Future Cop LAPD 1998. Yeah. Yeah. So yeah. So let's say you got a triangle here. Yep. And so do you color it or not? Right. For every pixel within the boundary. Right. So you can have an AABB surrounding the triangle. You just go through it, and you just say, like, is this pixel within the bounds? Is this pixel within the bounds? Is this pixel within the bounds? And if it's within the bounds, you color it. If it's not, you don't. And then there's some finicky rules, or not finicky, but like there's different approaches you can take in for like, what if it's partly, what if it's partly in and what if it's partly out? If you're doing anti-aliasing, you can anti-alias it based on what fraction of the line covers that rectangle, right? So here you can see the squares that are mostly covered by the line are darker gray, that are fully inside are black, that are partly outside are a lighter gray, right? And so that does a nice anti-aliasing effect. If you don't do that, if you just say it touches any part, or at least 50%, that's a common rule too, then you'll get this like jaggedy stair-step pattern, like this. And this is rasterization, right? So you can just basically go through every pixel, be like, is it inside? We talked about that last time, how to tell if something is inside of a triangle or not. So you can do 3 cross products. That's one way of doing it. Another way of doing it, if you want to see if something is inside of something. Let me save this here and open it up into MS Paint. Where did I save it? Downloads. Let's put in pictures. Here. Right click, open with MS Paint. Paint 3D, why not? We're in the future now. Okay, so check this out. So if I want to see if this point here is within the triangle, I can 2D shapes, line. I can just draw a line like this. And remember how we talked about the line intersection test? Depending on what's faster, if you can do 3 cross products faster, that's faster, or you can do 2 line intersection tests, basically, right? So you just basically see, or 3, you might have to do 3. But basically, you just draw a line across, and it actually doesn't matter which direction you draw the line in, as long as it hits the pixel. If it crosses 2 lines, it's within the triangle. You guys see that? So if we're talking about this point right here, it doesn't matter where I draw the line. Let me draw it like this. It doesn't matter. It doesn't matter which direction I draw the line in. You probably want to access the line to make the math simpler, right? Do you see that? If it crosses 2 lines, if it crosses the line, hits the point, crosses the line, it's inside. Okay. If it only hits, and this works on all polygons, not just convex holes, actually, right? Because you could have something like this. You can have like some weird like W-shaped thing, right? And if you have a point here and you draw a line, you start outside, right? You cross the line, you're inside. You cross the line, you're outside. You hit it, I'm outside. Okay. If I do it this way, I start outside, I cross the line, I'm inside. I cross the line, I'm outside. I'm outside. It doesn't matter which direction you draw the line in. You just remember, okay, I've crossed the line, I'm inside. Boom, there's a point, I'm inside of it. And you keep going, and outside again. So it's called the line crossing theorem. It's pretty cool. It's pretty cool stuff. You can use this basically with any polygon to see if you're inside of it or not. Does that make sense? So you just draw a line, boop, and you do the line intersection tests, and see if you're inside or not. That's safe. And you can do that for every point. And was that a watt? Did I get a watt over that? Did I get watted over the line intersection thing? Yeah. It kind of was like, yeah, I guess that does work, huh? You know, if you start outside, then you start from an infinite distance, right? So infinite distance is always going to be outside, right? Cross the line, you're inside. Cross the line, you're outside. Just keep track of that. There are 6-7 pixels extra. What does that mean? There is 6 or 7 pixels extra. For which one? For this? Yeah, like right here, it's crossing even a little bit. So they're using a rule here, where if the line touches it at all, then it is inside, or it's rasterized. So the thing about triangle rasterization is that you've got a triangle, right? And if it's a big triangle, then it's going to have to rasterize a lot of pixels, right? So if you've got a 4K resolution and you got a big triangle, it goes through every single pixel inside of that triangle, and it draws it to the screen buffer. Okay, a screen buffer is just a 2D array that is like what's going to be drawn on the screen. So for every X, for every Y, for every row and column, there is a red, green, and blue value, right? So yeah, I like it too. It's kind of cool. So if we have 8 bits per color, so that means there's 24 bits per pixel. And if we've got, what's the actual 4K resolution? Um, 3084 times 2160. Okay. So 24 bits per pixel times 3,840 columns times 2,160 rows is that many bits. 24 bits per pixel times the number of pixels. So if we divide this by 8 to get bytes, this is 24 megabytes. So every frame is going to be generating a minimum of 24 megabytes of data. And you want your thing to be running 60 frames a second. So that's going to be, what was that? 1.4 gigs, is that right? Of data a second. It's a lot, you know? And that's just to send 60 frames a second at 4K to your screen. That's just your final output, 1.4 gigs a second. Does that go to RAM? No, it's not in your computer's RAM. It's in your VRAM. So your graphics card has a VRAM, video RAM. and it's very high speed, and it has to be for this reason. Because this is just the output. This is just what it's sending to the screen. And your monitor is reading it. And a lot of times your interface isn't fast enough. I have an HDMI connection attached to my 4K screen here, and it can't actually do 4K at 60 frames a second. It can do 4K at 24 frames a second because the HDMI interface is not fast enough. It's an older HDMI. And I'm like, why would you make a 4K monitor, I don't know, with an old interface on it? I don't know. It doesn't make sense to me. There is a DisplayPort. DisplayPort on it will do 4K at 60 hertz. My other monitor, which has currently been sent back to ASUS for warranties for almost 2 months now, they broke it, and they're trying to decide if they're going to fix it or not. That one has a DisplayPort. It's a 120 hertz 4K monitor, but the DisplayPort cable can only support up to 98 hertz. So divided by 60 times 98. That's the maximum bandwidth on the DisplayPort cable that I have, 2.5 gigs a second. It can't do it. The screen could theoretically draw 4K at 144, maybe it is, but the cabling itself can't handle it. So, or maybe that's with HDR on or something. Yeah, it's kind of annoying. Like it's like, why would you do this? Modern HDMI 2.1 is capable of driving 8K at 60 frames a second, or it's capable of driving 4K at like 144 or 180 or 240 or something ridiculous like that. So the new standard is HDMI 2.1, and it does have enough to support high-speed 4K monitors, but do they support it? And more importantly, are they in stock? The answer is no. The answer is no, they are not in stock. It's legitimately impossible. Because I was actually going to buy another monitor because I sent it in for a warranty repair and they broke it. The fan was going out on it because it has a fan because it overheats because it's processing so much data.
And they're wanting you to pay for it.
And yeah, they're like, yeah, to repair your monitor, it's going to be $1,500. I'm like, no.
You were the ones who broke it.
No, it's under warranty. You broke it. You fix it. And so they've been sitting on it for a month and a half now, trying to decide if it's FedEx's fault or not.
It is its fault.
It probably is. Who knows? I don't know. I don't know whose fault it is. So, it's not mine. That's all I can tell you. Let's see. Components.
Don't order it until they fix it.
Yeah, so I had to buy a new monitor, but I was trying to find one. Computer systems, monitors. Here we go. Gaming monitors. Okay. And so I would like to have a high speed, let's see, 144 hertz, or up 240 maybe, at 4K resolution. And there's this many of them. Right? There's not a lot of high-speed monitors. So this is 43 inch. Interesting.
You're 43.
Oh, it's a 43 inch monitor. It's a big ass monitor.
Yeah, don't curse.
Sorry. Maybe I'll get that one. It's $1,500 though. It's pricey. 43 inch. That's a size. So I bought a TV because I figured I'll just get a cheap TV in the meantime. I can return it until 2 days from now, so maybe I'll return that. Get this one. 144 hertz. Oh, it's not HDMI 2.1. It does have HDR on it. Is G-Sync compatible?
Why are you buying screens while you're doing class?
Because this is relevant. Because this is what we're talking about, actually. So, yeah, I'll have to look up to see if it even drive that much. Because here's the thing, when that's just the output to the monitor, right? What you're actually doing is every time you have a triangle, let's say you have two triangles that are in the exact same place, one's here, one's behind it, you have to rasterize both of those, okay? I am using a TV as a monitor right now. Yeah, and it's like everything I was looking for was out of stock, and I don't really want to pay $1,600 for a new monitor when my monitor works fine and they're just, I don't know what they're doing. So let's say you have two triangles on top of each other. What's going to happen is that they're both going to rasterize onto the same place. And so what you're going to run into is a limitation on your graphics hardware called the fill rate. The fill rate is how many pixels it can push into the frame buffer per second. You have to divide that by 60 if you want 60 frames a second. And so there's a limitation on how many triangles a second you can draw, but there's also the fill rate, which is how many billions of pixels per second it can draw into the frame buffer. And if you draw it onto the same place, well, how do you handle that? Like if you've got two triangles and one's in front of another, which one gets drawn? You know what I mean? Yeah. So this is there's a lot of steps to rasterization, by the way. You first figure out where the pixels are. You do colors, lighting. You grab textures off disk. You use the UV mapping from a texture to figure out what the color is. You use the normal map to figure out how much lighting it should get. There's a lot of steps that take place in the rasterization pipeline. There's a lot of steps. I'm just sort of going over the basics right now. So if you have two triangles, one's in front of the other, which one gets drawn? Right? Here's a good example of it. What do you guys think?
How many more minutes do we have?
Until you finish your worksheet, girl.
No, until you're done with class.
Once you do your workbooks. So.
No, seriously.
Yeah. Are you done?
No.
Then do them. We can go.
Why are you waiting for me to do all my work?
Do your workbook, girl. Come on. So yeah, the one in front will be drawn. But what happens is that it rasterizes both of them.
I've already done 2 days of the same work.
Okay, then it'll be about 20 minutes. Okay. So what happens is it rasterizes both of them to the frame buffer, but then in addition to the red, the green, and the blue that gets drawn there, and those numbers again come from the texture, the material, the lighting, which involves a normal map. There's a lot of steps that go into like putting a pixel into the frame buffer. There's also something called the Z buffer, or the depth buffer. And so there's another 2D array that holds how far away each of these pixels are. Okay? And the one that is further away gets occluded, it gets overridden by the one that's nearer. So it doesn't matter which one you draw first. When you try drawing two pixels onto the same location, it looks at the Z buffer, says, this one is 5 meters away, this one's 10 meters away, draw the one 5 meters away. Do you guys understand? You guys get that principle? So whichever one, yeah. So P1Z is less than P2Z, so it's the one that gets drawn. Okay. But if you have like 1,000 triangles all in the same spot, it's going to be constantly rasterizing over that spot over and over and over again. And so you can actually saturate your draw limit, like the number of billions of pixels per second, with even just one triangle visible on the screen. So that's why it's really important for game engines to try and cut down overdraw. Overdraw is when you draw over the same spot over and over again. And there's all sorts of fancy tricks they use to try and figure out if something is occluding something else so that you don't need to draw it at all. They do pre-calculated visibility testing and all these kinds of things. But that's kind of the basics here. And we talked about Z buffer conflicts before, right? So Z buffer conflict is when two things have the exact same Z value. Z is how far it is away from the screen. Depending on rounding, because they're floating point numbers, it'll sometimes draw one, it'll sometimes draw the other. They'll sometimes flicker on top of each other. And this actually is fairly common because people will often snap to grid, right? And so they'll be at exactly 0 meters. And if they're if they overlap at all, and they're at exactly 0 meters, then you're going to get a Z buffer conflict on it. And they flicker back and forth. It looks really bad. Okay. Yeah. So back in the day, we would just rasterize the lines, and then later on, as technology advanced, as we got better hardware to do hardware acceleration, we would rasterize the entire triangle, or in this case, a polygon, I guess. So rather than line rasterization, we do polygon rasterization. Now, your next assignment is going to be a line rasterization. Okay, so you are going to just have to do this. So for each of your Voronoi regions, you are going to draw just the edge. Okay, just the edge. Not so. Right now we're filling it, right? But we're going to walk you backwards in time, and we're going to do line rasterization because it looks cool. So, so let me show you what it'll look like when you finish it. In the image of P1 and P2, the computer will draw P1. Yeah, whatever's closer gets drawn. Okay, so let's see if I get my password right. Good. Okay, so let me show what it'll look like. cd edgelord.reference. This is for you, Mason, edgelord. So for this one, it is the same assignment. It's going to randomly generate a map. Do you wish to do a running relaxation? Sure, why not? It's a little too much. Say no. Q to quit, sorry. Let's run it again. Let's see if we get a better map. There we go. That looks nice. Okay, so for this one, you are going to draw just the edges. Okay, so we're taking this kind of in the backwards order because before we had full polygon rasterization because we're just filling, right? We're going through every point normally and filling it with who owns it, you know, and filling it with a color. And we're going to go from there to line rasterization. Okay, and new Rocket League DeLorean time machine. Why are you giving me ads? Settings. Let me turn off the ads real fast. It's really annoying. News and special offer, free game notifications. I do not care. Okay, so so we're going the opposite direction from the normal approach. We're going from a triangle or polygon rasterization to a line rasterization. Okay, and so you just have to draw the lines. And so if it's a vertical line, you're going to draw a vertical slash. You see that? If it's a horizontal line, you're going to draw a horizontal slash. And if it's anything else, you're going to draw a plus. Okay. So on this boundary here, it's at like a 45-degree angle. It's pluses along the way. Yep. And so the algorithm to do that, every time there's a diagonal, there's a plus. Yeah. So the algorithm to do that is pretty simple. You just look at who the neighbors are. Okay. So for every point on the map, you look at the neighbor to the north, the south, to the east, to the west. If your neighbor is you, owned by you, you know, like if I'm this spot right here, you know, I can't really highlight it, but if I'm like right here, I'm purple. The tile to the north is purple. The tile to the south is purple. East and west are purple. Don't draw anything. Draw black. Okay? It's only if one of your neighbors is owned by a different country that you're going to draw something. And so if your neighbors to the east and west and north are you, then you draw a horizontal line. If your neighbors to the north, south, and west are you draw a vertical line. If you got neighbors in two directions, you draw a plus. And that's your assignment. Okay? So just take your existing Veroni relaxation algorithm and just change it. All you're going to do is change the draw world algorithm. You're going to change it to do edge detection. And edge detection, what? Yeah. This is actually a really useful algorithm. Edges are really, really important in computer vision, in autonomous driving, human vision, things like that. And we're almost done, bro. I'm giving them their assignment. So how do you find an edge? Well, an edge happens where there's a discontinuity, right? Think about it. Like if I don't know, looked at this title bar up here, right? It's white and it's black, right? There's a discontinuity between the white and the black. That's the edge. And so when you do edge detection, what you're basically doing is you're just going and you're just looking at the difference between two pixels. So if you're doing horizontal edge detection, you go one pixel at a time, and anytime you find one pixel that is significantly different than the one before it, that's a threshold that you set. In this one, it's very easy. It's just, are you me or not? You know, it's pretty easy. But like in a, if you were doing edge detection on like, edgy, yeah. If you're looking at like a natural image, then Lena, it's the classic. This photo was used in a lot of image processing. It's like the reference image, and then people figured out it was like from like there's actually more to the image, and so they kind of stopped using it. So what they did when they're processing these things is if you difference each pixel to the right of it, If there's a big jump, that's an edge. Congratulations. And so all this thing is here is all these outputs here. The white is where there is a discontinuity, a big jump in the color difference between one pixel and the other pixel. And you can do it horizontally, and you can do it vertically. And then there's better methods as well. I've looked at canny edge detection as well in the past. But that's a basic idea, right? So if you see the edge of the cliff here, it's just going from an area where it's white to dark, and so that's an edge. And then the output of these edge detection algorithms is used for image recognition, right? So you can tell that guy's wearing sunglasses, he's got a hat on, right? He's holding up a watch, and you can see the watch has all this detail in it, things like that. So,
wait, where's the guy with the watch?
Right here. So you see the watch right here. So the watch has all sorts of edges in it. So each of those little lines is an edge. The clock face is an edge, that kind of stuff. So you see there's a ton of detail in that. But yeah, the simplest way of doing it is you just see where there's a discontinuity. If there is, that's an edge. And then where the edges kind of come together, that's literally how the human visual cortex works, is that we actually look at edges to determine shapes, right? So when we look at this picture of a dude with a tripod and a camera, we immediately see the tripod, boom, 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 and we group that into a shape. And then our image recognition works at the shape level. So like when we look at a stop sign, what the human brain does is it actually breaks it down into each of the component parts. Line, some words in between. And when we recognize a stop sign, it's based on the color and the shape. So you don't even have to read the stop, right? It's just we've broken it into the parts, and when we see those parts come together in the same way, our brain goes stop sign. Like, you don't read stop signs usually. You're driving down the street, like, you don't need to see you're not like, I don't know what does that say? You know what I mean? Like, you don't need to read it. Your brain instantly recognizes it, And unless there's something really weird about the stop sign, you don't even pay attention to it, right? Like, okay, this one's got flashing lights on it, right? But by and large, your brain is just like, okay, it's an octagon that's red, it's a stop sign, right? Boom, right? And so there's a hierarchical system of the visual cortex, which is in the back of your brain over here, is structured into different layers. And it starts off by just processing the raw data, then it filters it, then it does edge detection, then it groups the edges into shapes, then it does object detection. And it's this very interesting, very fast process. Like, we can actually do it much faster than a computer. So in an autopilot, they only look at 3 points on a stop sign. Okay, so what you're going to do is just that. So it's same code, you're just changing the draw function. So rather than drawing every tile, you're only going to draw tiles where there's a discontinuity, where one of the neighbors, north, south, east, west, is different from you. And you just have to use, be like, is the different person to the north? If so, it's a horizontal line. Is the different person to the south? If so, it's a horizontal line. If I got two different people, one to the east, one to the south, it's a plus. If the different neighbor is only to the east or west, it's a vertical slash. So there's going to be a couple if statements in there to make your lives interesting. Probably shouldn't be more than 10 lines of code or so, thereabouts, order of magnitude, 10 lines of code, somewhere around there. So again, screenshot it, send it to me, and this should give you a really simplistic introduction to edge detection. And it looks kind of cool. I think this map actually kind of looks more interesting, I guess, than just a solid polygon, And they do this in some video games too, like random map generator. There's a really nice one that I was looking at. Maybe it's that one. Yeah, you see that? So you see how they draw the edges of each kingdom? Mm-hmm. The Duchy of Erase. Elfalis. The Grand Duchy of Nithil. So where the edges are, you see how they put like a little dotted line there.
Is that a real?
No, it's a random map generator. Nithal, yeah. The kingdom of Thinizlid. So.
What is this made of map?
It's probably actually kind of looks like it's with Veroni regions. You see that?
What's Veroni region?
It's the this thing that my students have been making. It's a random map generator for video games. So if you look up here, doesn't that kind of look like it? Kind of does, doesn't it?
Principality.
I don't know. Like the. Am I am I off base here? Because it kind of looks like these are just Veroni domains in here.
Kingdom of Paradise.
The Rokunis theocracy. Gloom. I want to change it to Gloom. There we go. Wow, that's cool. Did a whole palette swap on the whole thing. That's really cool. Yeah, but you see what I mean? Like, the edges are all highlighted, with little dashes. And if they're horizontal dashes. And if they're vertical dashes. So instead of a plus, they have an angle. But we're working with ASCII, so, what can you do? Okay. The Quegian Empire is giving you Russia vibes, yeah. Their capital is Kolb, which is the name of one of the most famous C++ people out there. John Kolb, leave page. Okay. Good. You guys understand? Nope. Oh yeah. Oh yeah. Yeah, we'll do this next. We'll do this next.
What?
Conquest. Geneva conquers Frankfurt. Madrid conquers Indianapolis. When you merge together multiple Veroni regions, you can get more interesting shapes than... Because Veroni regions tend to be sort of boring convex hulls, And so if you can merge together different regions, you can get more interesting terrains and things like that. Geneva is conquering Vegas. Geneva conquers Hong Kong. Geneva wins!
Except for that tiny part that you did not conquer.
Okay, we'll do that next. Don't worry about that for now. Okay, you guys understand? So just implement a change to the display output, do some edge detection, and screenshot it, attach it on canvas, call it a day. All right, so I'll push it out to you guys. See to deploy homework to IS50 edgelord. And then the conquest code we'll do next. Okay. When does it due? Tomorrow. It's like, I don't know. Doing it edgelord. Yeah, you have a print world already, right? All you have to do is, rather than just outputting the color of it, just check to see if the neighbors are the same color. If they are, print black. Otherwise, you're going to do an edge. You have a few if statements to see if it's horizontal or vertical or plus. 1, 2, 3, 4, 5, 6, 7, 8 lines, looks like. Yeah, 8 lines of code added onto what you have before. So, not too bad. Just if statements. Yeah, it's really, yeah. All in the print world. That's it. So in print world, rather than outputting the color of the tile, before you do that, you check to see, you get your color, you get the color of the person above you, below you, left of you, and right of you. Make sure you don't go out of bounds. If you're on the top edge, crash. So you get the colors of the people around you. If they're all the same as you, output black. If any of them are different, then you have some if statements. Is the different person east, north, south, west? And that's just to choose whether you're outputting a horizontal or vertical slash or a plus. So a couple of statements to figure out which character to print, and then you print your color with that character on it. So the foreground color will be black. The background color is your country's color. You guys, is it really that hard for you guys? Because I don't know. Yeah, like I don't know. It's just a couple if statements. Grab the color of the people around you. All day. Okay. And whether or not you draw a boundary on the edges is up to you too. I probably would. If you're on the top edge, just be like, yeah, it's an edge. If row is 0, yeah, it's the top of the screen. Print an edge. If I'm at the bottom, print an edge, column 0, column max, print an edge. That way you don't have to worry about going out of bounds. Yeah, it's easier than the relaxation. Yeah, it's just a change to the draw world. You're mostly just turning it black. You know, just start with that. If all your neighbors are the same as you, draw black, call it a day. I added a little bit of optimization where I don't constantly change the background color. I only change the background color if the background color changed. It's like, rather than saying change background color to black, change background color to black, change background color to black, which eats up your bandwidth, it'll draw slower, which you can do. Like, it's not a big deal either way. But rather than do that, I just remember, hey, what was the last color that I drew? And if it was black, then I don't send that. I don't do that again because it has to transmit to you over the internet.
Daddy, can you write 9
No, we're done. We're done, girl. You saw the cool cache? Yeah. So you can keep that. You got it, girl. Okay, so that's it for today, guys. My daughter has successfully done her long division along with some cute artwork. I don't know if you wanted to show that or not, but I'm proud of my daughter, so I'm going to show it off. Okay, and I'm going to head back to Fresno now. Hope I've got enough coffee for the drive, and that's it. All right, see you guys tomorrow.